Hi everyone, this is our fourth session on time series modeling and signal processing. So in this session, what we are going to discuss is actually that ACF and PACF function and their graph with respect to AR model and MA model. So actually in last lecture, what we discussed is that ARIMA model. The ARIMA model is the combination of AR model and MA model. In that case, in this third session, we actually randomly pick some values for order P as well as order Q. We did some graphical representation to identify it. But this ACF and PACF graphs and this technique is much useful in order to identify this P and Q parameter in AR process as well as MA process. So throughout this lecture, we are discussing the value of ACF and PACF and how do we implement it and how do we decide the value of P and Q with respect to AR and MA model, right? So you all know that actually that autocorrelation function, ACF function, is the function where it calculates the autocorrelation in between the data points. For example, if you read this first sentence, the autocorrelation function define how data points in the time series are related. That is simply a correlation on average to the preceding data point in order to predict the next data point, how it associates with each other. Actually, that's what we are discussing in the AR1 as well, right? Not actually AR1, whatever the AR process, which means autoregressive process also. What is the autoregressive process actually? Where we use past data points in order to predict the point after that, data point after that. Then the P implies the number of data points that we are going to use in order to predict the next value, right? Then in the ACF function is an autocorrelation function which gives us the value of autocorrelation of any series with its length value. That's what actually we actually want, right? How the relationship between the previous values in order to predict the next value, right? Then this for your in order to recall what we learned before, I just mentioned what is the autocorrelation function and autocovariance. We discussed these things just to recall what is the variance and the correlation. Actually, autocorrelation simply the directional relationship between two data points. Then the when it comes to correlation, the scaled version of covariance. Then auto means the same data series or time series we are referring, right? Simply is that. Then this is somewhat of a diagram of ACF plot, right? ACF plot is autocorrelation function. Autocorrelation plot is a visual way to show the serial correlation in data that changes over time. Since this is only a function of lag k, y-axis represent actually the correlation and x-axis represent the lag. Actually in here, it represent in the lag. We know what is the lag, right? The difference in that case, in this place, there is zero lag, which means we are comparing the data point itself. For example, suppose like this, right? If we have some, right. Sorry for that. Right. This is time, right? Time 1, 5, 6. T equal 0, 1, 2, 3, 4, 5, 6, up to suppose n, right? Then what they are saying is it compare the lags. For example, in here, so time point 1, 2, 3, 4, and it compare in what autoregressive model does is, suppose if you want to predict that 6 point, how many previous points that you are going to predict, like this the difference, right? Then likewise, once it comes to here, you can see actually there is somewhat of a gray area as well, right? You can see that this blue color area, actually it's not the gray area, blue color area, where it's the confident interval. You know what is the confident interval. So usually we set it to 95%, and there is some abnormalities of 5% as well, right? Then in the ACF plot, determining the Q value can be done like this, right? Because I stated that ACF plot is responsible to determine the Q parameter of moving average process, right? Then in the ACF plot, we can identify what is the possible Q parameters like this. For example, suppose this is the signal and we have autocorrelation function like this. In that case, there are some spikes, right? The correlation values, and in this blue area, some spikes inside this blue area and some spikes are outside of this blue area, right? Then actually this blue area is the confident interval. Suppose it's 95%. Then you can see it's like in here there are two spikes outside this confident interval value. In that case, we have to select these two, right? In here leg 3 and leg 6 as the Q parameters, values for Q parameter in the MA process, right? You know that in the MA process what we are doing is we are considering the error component rather the past data values, right? In the error component sense, how the relationship between previous error component in order to predict the next value, right? So let's see how do we implement it in the Python code base, this ACF plot and the PACF plot, in order to test the moving average process with ACF plots, right? Actually in the ACF plot, what we are doing is we are going to identify what are the number of previous error component we have to consider. That's simply what we are going to do. Then I have just borrowed this code from previous session because it's useless to write this again and again. Then I'll get another cell. Then what we are going to do is here that we are going to practice first. Suppose we are going to practice this ACF plot, somewhat of random noise, right? I think you can remember the equation of this MA process. It likes this, right? So it's something like MA process, because in MA process we are considering the error component. Then it's like this actually. So we have what is YT. Then we are considering previous error values. Then there is somewhat of a bias term as well. Then what else we had? Epsilon T, right? The noise component. And what we are going to do is we have theta value. Sorry for my handwriting. And epsilon T minus 1. Then what would be the second value? Theta 2 epsilon T minus 2 and something like this. Then plus theta times, we are going to the up to Q level, right? Then epsilon T minus Q. That's the equation, right? Then suppose we don't have anything. In that case, what we can do is actually, so in that scenario, it depends on with this is noise, right? This is noise. Actually, all those things we discussed in the last lecture as well, right? I just want to recall them only, right? So then what happened in here, actually in the ARIMA model, we discuss further like this, right? In ARIMA model, we have three parameters. So in ARIMA model, we have three parameters. What are they? P, D, and Q, right? Then right now in this MA model, we are talking on these Q parameters, past error components, right? Or noise. In other words, it noise, right? Then we are going to simulate it first. Then in very first time, for the easiness, let's consider actually some small random noise in order to get the very first understanding. Then I'm going to simulate it like this. So ACF with let's say random noise, right? It should be a marker, right? Then I'm going to get a fig as well as axis. Then I have import PLT subplot. I set some figure size into suppose 16 row and 8 columns, right? Then I'm going to plot the ACF one. Then actually it's available in this stat mode graphics TCA plot, and we have this plot ACF and plot PACF. We can directly import them, right? Then I'm going to import this plot ACF, sorry, plot ACF. Then what we are going to pass is actually it should be random noise. Then I'm calling that numpy randint. Then I'm going with the 1000 data points. In other words, 1000 timestamp in time series process. Then I set this AX as that our defined AX. Then let's see what is that. PLT is not defined. Did I import PLT? Let me check again. Right. Somewhat some libraries did not import it. Anyhow, okay. Then just give me 1 second. Right. See, this is with somewhat of a random noise. We are just representing some random noise. In that case, actually, we are just considering this epsilon t part with respect to this, right? Then what we can see in here, I have said that in here this is the confidence interval level, this light blue color, and these are the lag values 0, 1, 10, 15, 20, 25, and 13, and so on and so forth. Then we can see in that vertical line, this is the correlation 0, 0, and 1. You can see at lag 0, the correlation is 1. That's obvious, right? You can understand because it's comparing the same time series data point with itself. In that case, correlation coefficient is 1, right? But in the other places, you can see all correlation coefficient is within the confidence interval. Then that's obvious, right? That's what we are expecting in here because it's a random one. There should not be any correlation anyhow, right? That's what it is getting with the different lag values, although there is no any correlation between the next value, right? Right. I just want to let you know that what is the correlation and things in here, right? Sorry, autocorrelation function. Then how do we interpret it, right? That's right. Then let's try with somewhat of a non-value like MA1 process. So what would be the MA1 process? How do we define the MA1 process? Let's simulate MA1 process with this ACF so that we have to identify what would be the lag value, right? Then what is the MA1 value first? Let's see this, simulate the process, simulate MA1 process with ACF. Then it should be amount. Okay. All right. Let's discuss this. All right. So, according to our equation, what is the MA1 process? MA1 process. MA1. Then here Q equal 1. Right. Q equal 1. Okay. Then the equation would be like this, right? YT equal, I actually omit that error component, bias value, right? I'm just considering the epsilon only, epsilon in the sense noise component here, right? Then it would be like this, theta 1, right? Then epsilon t minus 1 plus the noise. Both the noise. Then in the MA1 process, it is considering all the one previous error component, right? This one. And the existing error component on this. So that's the only thing that they are concerned. Then let's simulate it with the Python code. Then how do we simulate? Then there should be errors, right? Errors. Then I'm going to implement it with the 0.1 standard deviation. And I'm getting NP random. And again, I'm calling a rand int. Let's go with the same as previous 1000 data point. Then what else we want? Then we have error with the normally distributed with the standard deviation is 0.1. Then there should be a list to hold or array to hold all these MA1 values. Then I am iterating this into 1000 times, right? To make the simulation. to make the simulation. Then here what happened actually at the zeroth point, what happened at the zeroth point? There is no any previous value or previous error component. Then we have to check it, right? Then if I greater than or equal 1, what we have to do is we are just calculating the y value or yt value with some coefficient with these errors, and we are considering what? Just the previous. Then I think you can understand this one, right? It's actually the same equation in here, the same equation, right? Yt, y, then theta 1 is 0.1. I just put, you can play around with other numbers as well. Then epsilon t minus 1, that means just previous error component. Then I minus 1, then noise of that ith index, right? I think it's clear enough. Okay, then what we are going to do is, that's fine, if else, then else in the sense I equals 0. At that time there is no any other previous values. Then we have to set only the noise only, not the previous current noise. Then y equal to this part only. Okay. Then I'm going to append these values to MA1 process. Then I convert it to as a NumPy array. Then it's easy to plot. Right. What we have done in here, we are going to simulate MA1 process, right? We are going to simulate MA1 process. MA1 in the sense we are just considering only one previous error component and with the current error component. That's what. This is the equation. Right? This is the equation that we are going to simulate. Then we have to consider two extreme cases. One is what happened at the zeroth index. We all know that at the zeroth index there is no previous error component. In that case, we just consider the current error component only. Other than that, if ith value is greater than or equal to 0, we have to consider the theta value with the previous error component and we calculate it. We append it to that MA1 array and we convert it to the NumPy array. Very simple code. All right. Okay. Then let's go in. Actually, let's plot it. PLT. You can get a figure. Then set some fixed size. I'm just going to copy the previous. It's easy. Otherwise, it's time consuming. Okay. Then I'm going to plot it. Sorry. Plot new one. Let's see. So I just plot MA1 first. Just want to see what it look like, right? You can see it seems to be stationary, right? There is no much deviated variation. Mean is like 0, and actually it's normally distributed because we are getting the normal one and standard deviation is 0.1. Right, there is no any seasonal component, randomly distributed, right? Okay, then let's print the ACF plot. Actually we can copy it from previous. Okay. Just paste. Instead of these, we can set what is MA1. It's pretty good, right? You can see we already know that, right? We simulating MA1 process, moving average order 1 process we are simulated. Then we want to check whether our ACF plot will identify whether it's a moving average 1 process, because we are simulating it, right? Actually, it has identified it. You can see at lag 1, we have non-zero value. We have non-zero value at lag 1, right? Then it is a moving average order 1 process, because we know that we simulate it, right? In here, we simulating order 1 moving average process. Actually, ACF plot represent it as well. Then what is the vice versa? Then we have real data. What happened actually in the application level, what we are doing is we have real data. Then we just plot that autocorrelation or ACF function. Then we identify what is the lag in order to define the Q value. Right now, we are going to verify whether it's correctly performed. Right? Okay. Then in this case, actually, it's right that. So you can see it, right? Then this is MA1 process, which means moving average with order 1, right? Then let's check whether the same thing is applied, or whether it's accurately happened to that moving average 2 process as well, right? Just verify it with the moving average 2 process. So what would be the should be moving average 2 process. So I'm going to simulate. Oh, may I change the same code? I think it's easy. Right. Then I'm going to change it to moving average 2 process. Right. Then what would be the equation? Let's think about the equation as well. Then at that time, what would be the equation? The equation should be like this, right? YT equal theta 1 epsilon t minus 1 plus what? Plus there should be 2 terms, epsilon t minus 2 plus epsilon t. Error term at t minus 1, error term at t minus 2, and error term at that time. That's what we are going to simulate. Right. Then we have to alter this one. Then I'm going to set it to 2. There should not be any changes. Then the 1000, that's fine. Then let's keep this one and error 1. Yeah, we have to add another one, right? We have to add another one. Right, I will set it to minus. One is plus, other one is minus. Then I set it to this 0.3, and it should be t minus 2. What else we want to change? This should be 2. This should be 2. This should be MA2. This should be MA2. Right. Good. Is that fine? Okay. Let's set to MA2. Okay. Right. Let's try. Okay. Let's print it. There is no much difference because we use same one here, right? And MT2 also same. There is no much difference with the previous one. This also is stationary. It seems stationary and around the 0 mean. And there is no much different variations as well. Anyhow, then this should be MA2 then, right? Then previously this is MA1 process. The ACF function very accurately identify that lag is 1. Let's see right now it should be lag is 2, right? Yes. Yes. You can see there are 2 points. 2 points are available, and here also you can see, right? some places like at lag 10, I think this is lag 9, 11, 12, there are some outliers, because I mentioned that confidence interval is 95 and there is a randomness of 5%. In that case, this can be happen. This definitely can be happen, but we can ignore them because it's somewhat of abnormal scenarios. There is no any much difference, actually significant difference like these spikes, right? These are just that some exceptions. So, but in here you can identify some clear cut, right? In the lag 1 and lag 2. That's obvious, right? Because we are simulating MA2 process. MA2 process. In that case, it should be lag 2. In here, 1 and 2. Then there are another thing you can see is that one is positive, other one is negative. Why is that? The reason is we simulate in here with the minus. Then let's see with the plus what happened. With the plus what happened. There is no any change with this time series. See, it become positive, right? Likewise. Then this is how we can simulate. In that case, we can identify that this is actually that ACF autocorrelation function definitely identify what's the exactly lag weight. In here, you can see again randomly there are some places, but we can omit it because it's very close to confident interval level. But these are significantly outside the confident interval level, these two. Then in here, you can play around with the lag 1 and lag 2, but it is better to go with the lag 2. Once you are making the process, MA process, then the Q variable should be 2, right? Likewise. Then you can actually simulate with the MA3 process as well, the similar thing you have to do. Only thing is what you have to do is in your equation, instead of these two, you have to add one more error component like this. It should be then yt equal theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2 plus theta 3 epsilon t minus 3 plus epsilon t. That's all. Then you can simulate it, right? If you want to simulate it, you can just have what you have to just alter. In here you have to add error I minus 3 with some random value here, plus minus you can play around, then check whether what happened, right? So that's actually that which is called ACF plot, right? So if we recall what we discussed up to now with connection with the previous session, previously we discussed about ARIMA model. In ARIMA model, there are two components, basically three. There are three actually, but there's basically two processes. One is AR process and MA process. Then in here, we discuss with respect to MA process, how do we identify or select the parameter Q with using ACF graph autocorrelation function. So it is helpful. It can be used to determine the Q variable. The way of determining the Q variable we discuss and simulate it with this code base. Then you can simulate for MA3 as well to identify that value, whether it's definitely or correctly identify the lag, right? We check with the very simple random